see this one, is a P max minus P road. If you see, I said P make or P shaft, but maybe some books, they put, I'm not sure the book we have defined it this way or not. P shaft is what is transferring to the shaft. So after the rotational loss we have, if you see these things, don't get confused. You see, P shaft is different from P mechanical. Basically, it's minus the P rotation. That's the difference. We have this circuit. Per phase, this one, right? So in the IEEE, let me talk about two things first. There is an approximated circuit. Basically, they said, hey, like a transformer, you can move this one from here to here. App circuit. They draw it like this. RCXM. But the one IEEE is using is assuming RC is almost infinite, so you can get rid of the RC. So basically, the circuit, the one is used by IEEE, the standard, those kind of things, is this circuit without RC. So basically, it's like this. So either this one, or approximate circuit, this one, or the IEEE circuit, this one. Now, any of them, for example, let's go with this one, for example. Let's go with this one. What I want to find now, I want to find the torque characteristic of the machine. Remember, for the DC machine, we get the equation, we find out, what is the torque characteristic. My intention is to find the torque characteristic for this induction machine to see how it's going to look like. So, to do that, first I'm going to calculate, if I want to calculate the torque, let's put it here. Torque is going to be P max over omega m, right? Whatever power is going to the shaft, right? Dividing by the rotational speed of the shaft, right? P max over omega m, right? Keep this one. So in mind, before going there, I'm going to calculate the P max, right? If I can calculate P max divided by omega m, I can find out the torque, right? But how much is the P mechanical? Tell me. How much is the P mechanical?
P shaft minus P rotation.
No. Let's say P rotation is 0 for now. So P shaft and P make, they are the same, right? But what did you have a question?
Oh, I was going to say P out minus P rotation.
P, yeah, no. So look at this circuit. See, this is the shaft here, right? Shaft is here, right? Basically, here is the air gap, right? Air gap. And this is the P shaft, right? The power is coming through the air gap here, some will be dissipated here, and after that it's going to go here. So basically P make is here, right? The power in this resistor, right? This is the P make. So it's going to be 3 times, let's call this one I prime R. 3 times I prime R to the power of 2 times this resistor, right? You have it in your note from Tuesday. If you look at it, you have it from your note in Tuesday class. So this is a P mechanical, right? This part is clear. There is nothing to calculate. But I want to calculate the I prime R. I want to calculate. See, the things are known. I have a VS over here. Let's put it here. I have a VS, I have a RS, I have an XS, I have all these parameters. I want to calculate the characteristic of the machine based on all these known parameters, right? So I need to go calculate the I prime R, right? Let's go with the Thevenin. Let me put this extend here. I'm going to go with the Thevenin circuit in here, from here. I'm going to find the Thevenin equivalent circuit. So I can go replace all this one, right? Everything I have here. Or I can use the IEEE one, doesn't matter. Or I can use the approximate one, either one, right? Whatever. I'm going to go from this point, right? Whatever circuit you are using, I'm going to go from this point. Right? This from the air gap side to that side, right? We got here from this side, from here. If we calculate the Thevenin circuit of that part, what we are going to see, we are going to see this. We are going to have a V Thevenin, right? And there is a Z Thevenin, which is going to be R Thevenin, and there is the X Thevenin, right? You pronounce it Thevenin? Right? Okay. So, and the rest of the circuit is going to be here. And this one was the R prime R. Right? The reason we show it with a variable resistor because S can change, right? So this is not a fixed resistor. Based on whatever is the value of S, this one is going to have a different values, right? That's the reason I'm showing it that way. Now, so I assume, let me put it this way. How much is the Z Thevenin? Somebody tell me. How much is the Z Thevenin? I'm going to go with this one, the most complicated one. Let's go with this one.
XM parallel with RC and parallel with RS plus X.
Yes. Basically, this one we should be shorted, right? This impedance, right? Parallel with this one. Let's call this impedance Z phi. Z phi, that's the excitation. So 1 over Z phi is going to be 1 over RC plus 1 over JXM, right? I call this one Z phi. This branch, I call it Z phi, okay? So, Z Thevenin is going to be Z phi parallel with this one, right? So, Z Thevenin is going to be Z phi parallel with RS plus JXS, right? Right? Yes. And how about the V Thevenin? How about V Thevenin? How much is V Thevenin? Look at here. We have this voltage, one impedance here. Just I'm going to put here, you can look at it. See, I have a source here. There is a Z1 here, and there is a Z2 here, right? Z1, Z2, and Vs. This is a V Thevenin, right? So that's the voltage divider, right? It's going to be this one divided by this one plus this one times this voltage, right? So it's going to be Z phi over RS plus JXS plus Z phi, right? Time Vs, right? These are the Thevenin values for this system, right? The Z phi over RS plus JX plus the Z phi times Vs. Now, if we go with the IEEE circuit, basically it says RC is infinite. It says RC is infinite. So basically Z phi is going to be JXM, right? And you can kind of, summarize this one. I'm going to talk about the IEEE circuit, later. So, but let's say Z Thevenin is going to be R Thevenin plus JX Thevenin, right? I calculate these values, V Thevenin, R Thevenin, X Thevenin, based on this circuit later. I'm going to finish my calculation. I'm going to calculate, I'm going to tell you how much are those values based on this circuit later. So for now, let's say there is the R Thevenin, X Thevenin, V Thevenin, right? We have those values. You can go calculate it accurately using this equation, right? You can go calculate them accurately using this equation, or you can use the approximate models, to calculate them. But for now, I'm not focusing on that part. We'll calculate those Thevenin values. Now, if I have this circuit, and I said I want to calculate P mechanical, right? I need to calculate I prime R, right? So it's a very simple circuit, right? How much is I prime R? It's going to be V Thevenin divided by all this impedance, right? So I prime R is going to be equal to V Thevenin over, I'm going to write it together, R Thevenin plus R prime R plus R prime R over S times 1 minus S, right? Plus J X Thevenin plus X prime R, right? So this one together is going to be what? R prime R over S, right? So basically I prime R is going to be V Thevenin X prime R. Before I left, we had about 60 students in the class. Now is 34. I'm not sure. Are they? They're off the course or they're not showing up? I'm not sure which one is it. Hopefully they didn't drop it. And so we have the I prime R. So to calculate the P mechanical, right? This one is what? This is the magnitude of I prime R, right? For example, let's say we calculated I prime R, for example, is, I don't know, 10 amps with 30 degrees, right? When you calculate here, this one is what? Is a 10, right? Forget the angle, right? So basically, I want to calculate the amplitude of I prime R. How much is the amplitude of I prime R? So it's going to be the amplitude of this one. So it's going to be V Thevenin. I don't want to put this sign everywhere, but I'll write it once. But later on, I'm going to get rid of it. When I write it, is a magnitude. There is no angle, But basically, it's going to be like this. So, and it's going to be divided by magnitude of this one, right? It's going to be RTH plus R prime R over S to the power of 2 plus XTH plus X prime R to the power of 2. Right? That's I prime R. Now, let's replace it in this equation, calculate the P mechanical. So P mechanical is going to be if you do this one, P mechanical is going to be 3 times this. It's going to be 3 V Thevenin. See, this is the amplitude I'm putting here, but just I'm writing it this way. V Thevenin times R prime R over S times 1 minus S, right? Divided by this. This one should be to the power of 2, right? It's TH plus. This is a P mechanical, right? This is a P mechanical. So we calculated P mechanical. So let's go calculate the torque now. Let's go calculate the torque. Torque is equal to electrical torque or whatever. P mech over omega n. So P mech is what we have here. Okay, let me put it a little bit down here. Omega m is the mechanical speed of the rotor, right? Is the mechanical rotor speed of the rotor. What should I put instead of omega m? Can I put, right? We said, you know, if you go check your note, we said n rotor, or n, is 1 minus s ns, right? That was the equation we had, right? The speed of the rotor is 1 minus s times synchronous speed. The one I put it with the index of s. So this one is synchronous. S stands for synchronous. That's a synchronous speed. And we know how much is the ns? 120. Ns is equal to 120 f over p, right? That was the number of poles, right? F is the frequency of the what with the frequency we are supplying the machine, right? And p is the number of poles machine has, right? Now, let's look at this one. This one is going to get cancelled with this, right? So basically, it's going to be 3, let me see how did I write it here. It's going to be 3 VTH times R prime R over S divided by what? This one is going to go omega S times the square root of RTH plus R prime R plus XTH plus X prime R. We find the torque equation, yes.
We can unplug that.
Sure, for P mech, shouldn't there be no radical in the denominator?
Yes, you're right. You're right. Yeah, yeah. Sorry. Thank you. So, I want you to know when we give you the homeworks, you are going to have the parameters of the machine. You are going to have the RS, XS, XM, R prime R, X prime R. When we give you the, or you can go look at the homework. You look at the books. Get one. There is a motor samples over there with the parameter. You know all these values for the motor. I want you to do this one time in your life. I have done it myself. I'm not going to do it again. But you do it one time in your life because I'm going to plot it here. I said it looks like this. Just go do it once for yourself to see, oh yeah, he's right. It looks like what he's putting it in the board. It's a very simple plot. You can go do it with MATLAB, plot that one. If you plot this one, torque is going to be like this. I call it T as a function of S. See, because there is a S here, right? We have an S here, based on how much is the S values.
This is a squared, right?
Yeah, this one is a square also. Yeah. So T as a function of S versus S, but it's a little bit weird. S1 is here, and S0 is here. See, the axis is this way. You can put it that way, but all the books they plot it this way. What does it mean S1? Let's say, what does it mean here? S equal to 1. What does it mean? Right? The machine is not moving. What does it mean S equal to 0? Yes. Omega m is equal to omega S. They plot it like this. S here, they call it, this is a starting point because the machine is not moving, right? If you plot this one, you're going to see something like this. Just have when you have this equation, put some value for the voltage, even 1, put it 1, Just change the S value and plot this one, you see something like this. This is the torque characteristic of the machine. Just I put the first quadrant, but this one can go like this also. Now I'm not talking about that. This one, when it's a generator, it's gonna go this way. We're talking only about this part now. Now, so there is one, the first thing you can see here, there is a T max, right? T max, and let's call this one S max. They call it S max. You know, there is another one I'm going to talk about it, but T max and S max relates to the sleep, which is going to generate the T max, right? Now, I'm going to make this one a little bit different. Let's make it this. Let's say, just I'm giving you an example here. Let's say this is a T load, and it's a constant. Could be a pump. If it's a pump is like this usually. Pump usually is like this. They are like this. The pump characteristic is like this. But let's say it's a constant torque, you know. So where the machine is going to work? At what speed or what sleep is going to work?
To the right.
Is that here? This is where it's going to work, right? Always, the sleep of the machine is more than 0. Unless we are at the no load. No load means where? Here, right? It's still at no load, think about it. It's still there is some load. There is a rotational loss, there is a resistive loss, there is an iron loss. These are like a fake load, right? Never ever we can get to this point. But ideally, at no load, we are going to be rotating at what speed? Synchronous speed, or S equal to 0, right? But as I said, no way we can go. For example, the closest one we can get is going to be somewhere here. Somewhere here, because there is still some load, you know, because of the losses in the machine, there is some load. Now, can you see any problem with this curve? The curve is correct, but can you see any problem?
When you're operating at like your standard load, if you increase the load too much, the motor's going to stall out.
It can, but that one is for everybody, you know, every motor. You know, if you go too high, the motor is going to stall, exactly. But no, my point with this one, you're seeing on the board, do you see any problem?
The starting torque is too high.
It's more than S max.
Huh?
It's more than S max when you have the load.
This one is more than the max, you mean?
Yeah, when you're at the load, your S is more than S max for the rating.
Right. No, but the problem is here.
Yeah.
This motor is not going to never ever is going to run if you put that kind of load on it. Why?
No number start.
Because the TL is more than, let's call this one T start. Motor can generate only this much torque, right? So it cannot run, right? So what is the load torque? The load torque, yeah. So we have what we have.
It won't start up later on halfway.
No, so see, you start from here, it goes there. We don't start from here, come back here, right? We are here. Let's say you are in the base, military base, and they say you jump over these walls, right? I don't know, something like that. There are like 10 of them in the rows, right? The first one is very tall. If you cannot jump first one is not like that, you can jump the rest, right? You have to jump the first one, right? And after that you can go there, right? So basically we are stuck here. What should we do?
Get a bigger motor. Add a capacitor to help you
We can get a bigger motor, but you know, it's not economical, right? See, I can handle this one. See how much load I have?
We bring
You can add a
a
capacitor.
certain point beyond that first, and then we put the low one.
Say it again.
We just bring the torch to like beyond that low, and then we put the low one.
You mean bring this one up somehow?
No, we start it first. Wait until the start.
Oh, you mean bring the load later?
Yes.
So no, let's assume we cannot do that. Load is already there. We cannot.
You can add a capacitor just to help start it and then shut the capacitor off once it's going.
That one is for single phase motor, not for 3-phase. They don't need a capacitor. How about, let's say, if somehow I can shift this one this way? How? I'm not going to tell you how, but right now. But if I shift it this way, right? Hey, here is okay, right? More than this, right? Remember I told you the starting of the machine? So basically, we're going to talk about this one, how to do this one, you know? So right now you can see the problem, right? let's get a little bit more to that. Let's calculate S max, let's calculate T max, those values, and after that, yep.
So torque load is defined as the torque required to make the load do spin, correct?
Yes,
Okay.
yes. This is the load we have is holding this shaft, right?
Yeah.
You have to apply a torque more than this initially to run it to speed up, right?
Okay.
When you get to the speed you want, the input should be equal to load torque. So basically, you're going to start rotate at the constant speed, right? Initially, you need to have more torque than the load torque to speed up the machine. Now let's calculate these values first, T max and S max, and after that we'll say how we can fix this problem without buying a new motor. You know, we can keep the motor and we can solve it. So let me see where I did calculate this one. No, I really passed the goal. Yeah. So, to find the S max, what should I do? To find the S max, tell me what should I do?
The derivative.
What is happening at S max? Torque is maximum, right? Let's go with this one. I said dTs over ds equal to 0, right? We calculate it this way. I'm not going to go through the calculation. If you do this one, you will get the S max. S max is going to be R prime R over R Thevenin plus to the power of 2 plus x equal, sorry, I put the equal here, x Thevenin plus x prime R to the power of 2. So if you take a derivative of the torque, put it equal to 0, find the answer, that's the S max. S is not maximum, don't get me wrong, you know, S is not maximum. But at this sleep, torque will be maximum. That's the reason I call it S max. It doesn't mean S is maximum, right? At this S, torque will be maximum, right? So we calculate that, that's I call it S max. Now let's calculate, so if you get S equal to S max, so basically replace this one here, right? We can calculate the maximum torque. T max is going to be and don't worry about this equation. All you can use it in your cheat sheet. Don't worry about this one. You know, you don't have to memorize anything. You know, don't think about it at all. V Thevenin to the power of 2 divided by omega s times R Thevenin plus R Thevenin to the power of 2 plus x Thevenin plus x prime R to the power of 2. Right? So we calculated T max and we calculated S max, right? Yes.
Which side do you want to be when you operate, your machine? Like, do you want to be at the maximum torque all the time, or does it depend?
No.
This depends on whatever.
Yeah, this depends on the load. It depends. The only thing is T max should be more than T load.
That's it.
If it's not, so let's forget the starting, right? Let's forget the starting. Basically, the area we are going to work is here, right? The operating point is going to be there, right? T max should be more than TL. If it's not, we cannot run the machine, right? That's not possible to run the machine.
Why not operate on the left side of T-max?
That one is not stable. That's not the stable side of the system.
What's the reason?
Stable, this is just a graph we put here, but let's think about it. You start from here, right? That's a synchronous speed, no load, right?
Mm-hmm.
Let's assume you're increasing the load, right?
Mm-hmm.
So basically you are going to move here, move here, move here, move here, move here. If you pass this point, how we can pass this point? So basically you went, see, you were here, 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 here. Now if you're going to come back, it's not going to go to this side. It's going to go back here. This is exactly the same thing for solar panels. If you look at the solar panels, also the characteristic is like this. P, we're gonna have this one in power electronics too. It's gonna be like this. This is where you work, not the left side. Now, let's go back to the problem I mentioned about the starting to see how we can fix it. Let me arrange this one to draw it again. Right. Let's look at the Tmax equation first. Is this one depend to the R prime R? Let's look at it. There's a V Thevenin, right? Omega S, R Thevenin. See, R Thevenin is going to be based on XM and RS and XS, right? There is no RR, right? R prime R. The same thing here. There is nothing related to R prime R. So what does it mean? This peak is independent of the value of our prime R, right? It's something, for example, 100, 200. So by changing our prime R, we cannot change our prime R, but let's say if even fakely we can change our prime R, it's not going to change this value, right? So the maximum is constant, right? It's not a function of our prime R. Now, let's look at this one. Again, the denominator is a kind of number, is not a function of our prime R. But look at here. If I increase our prime R, what's going to happen? S max is moving, right? It's going to be getting bigger and bigger, right? So if, for example, I make it double, it's going to come here, right? The new S max is going to be here, right? If I make it triple, it's going to be here, right? If I make it 4 times, I'm going to be here, right? So basically what is going to happen if, for example, I make it double, now my Tmax is going to happen here, right? So basically this one is going to be like this, right? If I make it triple, it's going to be like this, right? If I make it 4 times, it's going to be like this, right? So how did I shift this curve? Adding resistor to the rotor of the machine. If it's a squirrel cage machine, can I do it or not? I cannot. Why? Because I don't have access to the rotor circuit, right? All is shorted internally, there is nothing out. But if it's a wound rotor, basically rotor circuit simply, just I put the rotor circuit here. This is a rotor circuit, you know. Let's put it this way. For example, this is a X prime R, X prime R, X prime R, R prime R, R prime R, R prime R, right? I have these 3 wires available, right? It's not exactly correct, this circuit, but I'm saying something like this, right? I have these 3 wires here, right? What I can do is, I put the R, EXT, external here. The same thing here, R, EXT here, R, EXT here, right? Now, I put 3 resistors and keep this one shorted here. Right, short them here, right? In the squirrel cage machine, these are all shorted here inside the machine, right? I put an extra resistor here and I short it, right? How much is my rotor resistance now? Fake rotor resistance is R prime R plus R external, right? Right? So basically I increase my rotor resistance, right? So basically I shift this curve to the left. The peak, the maximum I shift it to the left, right? What is the problem with this?
More power loss?
More power loss, yeah. Because I rotor is going to go through this one, right? What should we do? We put the resistor there. When we passed, where is it? We passed the first, valve, right? We'll take the resistor out, right? We short it out, like the one we had it for the DC machine, right? Let's put it, for example, like this. For example, we'll have let's say 2-stage resistor, right? I put one of them here. Basically, and all they are connected. This is a 3-phase system. All they change together, you know what I'm saying? So we will put this one here. We start the machine, run the machine, and after that we go here, and after that we go here, right? When the machine starts, so after that there is no resistor in the circuit. But this one can only be done for the wound rotor machine, not the squirrel cage, because we don't have access to the rotor in the squirrel cage, right? So this is one of the big advantage of the wound rotor machine. So you can control the torque, right, with the external circuit. But wound rotor, they are much more expensive than the squirrel cage. So the other thing is adding this resistor. You can control exactly like a DC machine. You can control the starting current of the machine. Here again, when the machine is not moving, the starting current is pretty high. For the induction machine is 5, 6, 7 times of the rated current. So when I'm talking about this one, you're talking about 2 megawatt machine. Think about it. They have a 2 megawatt, 4 megawatt machines. 4 megawatt times 7 is 30 megawatts almost. Think about it, you know, what kind of the breaker you have to have, what kind of wires you have to have, how much problem is that, you know, to solve it. One of the best way to solve it is the soft starter we talked about with those teriyaks and those kind of things. You don't need to have access to the rotor. Just you increase the voltage slowly, right? Another one is they call it a star delta switch. I'll talk about that one later, but that one is not perfect, but it's better than nothing.
How do you fix that problem with a squirrel cage machine?
Yeah, as I said, you use either the variable voltage source, slowly bring it up, or they have a delta star converter. I'll talk about that one later, you know.
I meant in terms of torque.
So I mean, you're talking about this.
Yeah.
Yeah, I told you exactly.
Okay.
I'm saying either you cannot use this method for that one.
Yeah.
You use either the variable source, you know, to control this one, or you use they call it delta star, you know, converter. I'll talk about delta star later. But the variable source is power electronics. We're not going to talk about it here. But they have a delta star, you know, breaker, something like, I don't know exactly what they call it in English. I need to go find the terms, and for next time I'll tell you the right term, what they're using. But they use a delta star, you know, converter. I'll talk about that one later, you know. But for now, you saw what we did. We add a resistor to the circuit. We move this pick here, right? Now I'm good. I can start my machine. This is too much, you know, you don't have to put this much. This much is enough. After your machine is speed up, get rid of the resistor. Take it out of the circuit, right? So we get the S-max, T-max, and those things. T-max is going to tell you what's the maximum load you can put on this machine. Even if, let's say we calculate T-max is 200 Newton meter. We're not going to put a 200 Newton meter on this machine because they're going to be right here. System is not stable here, right? Usually we keep it like a 50%, you know, margin, you know. The maximum will go up to here. We don't want to go there, you know. These are all for stability purposes, you know. You don't want to go very close to the limit, right? So let's say you are a bank, right? And you put so you know your customers is going to be, they're going to ask you daily $1 million, for example, right? You have a coming to. You're not going to put exactly, this is your estimation, $1 million. You're not going to put exactly $1 million to your pocket because maybe today somebody comes with 1.1, you know, one small point. Now you're out of money, right? You cannot do that. So basically you keep some margins, you know. When they chain the banks together, that's the good thing is, you know, you don't have to have a reserve in all of them, you know. You will have, for example, 1 million here, 1 million here, 1 million here. So we can, online, you can move it here quickly. If you need this bank today has a 500K, you know, this guy has a 1.2, so just move 2.2K here, you know, so it's going to cover its customer. So they're like a big bank together, you know what I'm saying? Here also, we don't want to go here, because if small things happens, you're going to lose the control, right? The machine is not going to work anymore. If this one goes a little bit higher, machine is going to stop, right? So we calculated this value. One more thing I want to calculate is not very useful parameter, but I'm going to calculate it. I calculate the T-max. Now I want to know how much is the P-max for this machine. If you want to calculate P-max, how should I calculate it?
T-max times the megawatt.
Here, right? Let's take a derivative of this one. power electronics is the key to everything, you know. Believe me, nowadays is very, 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 very practical and, you know, useful to help to do everything in the system, you know. So if I want to calculate the P max, I said dP over ds equal to 0. Here to keep in mind, P is here. P is here. You have P here. dP over ds equal to 0. So let me put a better picture here before we go, you know, because I'm worried you're gonna get confused, you know, later. See why this one is here. If you are going to correct this one, put it this way. Let's call it R start. RST. RST, all of them. So basically it's going to be something like this, right? And these three, they are all moving together. This is a mechanical interlock, right? So basically you start from here, you have the maximum resistor in the circuit, you have the very high starting torque, right? And after that, the machine runs, you know, you move this one to the left to make it, oh sorry, you move this one to the right to short circuit the whole resistor, right? If it's here, you have the maximum resistor in the circuit. If you're here, you don't have any resistor in the circuit. Now, let's calculate the P max. So, P max will be, again, when we calculate this one, it's going to give me S of P max. I'm going to call it this way. Do not make it confused with that. That one was the S of T max, which we call it S max. S for P max is going to be R prime R but you know my style, right? No way I'll give you a question in the exam to use all these expressions. You can write it down and bring it, you know, I'm fine with that. But no way I'll give you a question to use all these big equations, you know, to calculate it. We're going to get to the simplified one, you know, later. In the example, that one, I'm going to, most probably the question is going to be using those equations. But you need to know these things all, you know, if you need to calculate the maximum power of the motor. So you have the S max. So if you calculate the S max now, you can calculate the P max. P max will be this is if you want to calculate the maximum power of the machine. So look at here, SP max is different from ST max, right? It's not going to happen at the same time. Maximum power is not going to happen as maximum torque, you know, keep in mind. It's not going to happen. Now let's get to some simple equation. We know T max and P S max from here. Because I'm going to try to find the one useful equation. You're going to use it for lots of, you know, starting, all those kind of things. Just I'm going to use the S max and T max. Let's say if RTH is very, very smaller than XTH plus XR. Let's go back over there, see what's going to happen. So look at here, let's start with the T max, right? What's gonna happen? This one will be gone, right? Compared to the, we said this value is very, very smaller than this value, right? So this one is gonna be gone. So basically it's just square root of this one to the power of 2 is gonna be R prime R over this, right? S max is gonna be how about T max? Let's see what's going to happen to T max. If, again, this one compared to this one is gone, right? Again, it's going to be RTH plus this, right? To the power of 2. Again, that part is gone, right? Basically, it becomes 3 over 2 VTH to the power of 2 over omega s times what? Times what? Let's see. Yeah, it's going to be XTH plus X prime, right? Right? This is the starting torque. This is the torque equation, maximum torque. Now, let's find the general, equation. Let's say T max, now, T max over T, what is going to be? T for any S, it could be a starting, it could be, I don't know, full load, half load, but for any S. This one is a TS, I'm putting here for any S. So it's going to be, T max is here, right? I'm going to replace this one. Let's go find out what's the equation for TS. Here is the TS, right? Is it this one? Yeah. This is the TS. So the TS is going to be again this one. It's going to be 3 times R prime R over S VTH to the power of 2 divided by RTH plus R prime R over S to the power of 2 plus XTH plus X prime R to the power of 2, right? Everything times omega S, right? I put this equation here.
Where did the R prime R over S come from?
Yeah.
Here.
No, the second one.
The R prime R over S
In the bottom.
on
Where did I put that?
the denominator?
Yeah.
Oh, there's no reverse.
Oh, so I made a mistake. That's
It's R prime
RTH
R.
plus R prime R. Sorry. There's no S here. There's no S. Now let's look at these two, right? So let's get rid of this one and this one. S is going to stay. There is a 2 here. Just I need to make sure. So there is a 1, this one, and this one, and this one. They're gone, right? Omega S is going to be gone with this omega S, right? So basically, it's going to be T and max over T at any S is equal to. So this one is going to go up there, and there's a 2 here, and this one times this, right? It's going to be 1 over 2 times, I put that one there, RTH plus R prime R to the power of 2 plus XTH plus X prime R to the power of 2, let me see if I put it correctly, yeah. Divided by what? Divided by R prime R over S. Did I do it correctly? Let me see. 1 over 2, I put it there. And this one is going to go up there.
Missing
Get rid of
XTH,
square.
X
But
prime.
something I'm missing.
Get
Yeah,
rid of
XTH
square
is
on
there.
there.
This one. Huh?
Oh, it's now.
Just put it on that.
You need to put
No, you have to put it on the bottom.
Yeah. This is the xth plus x prime r I'm missing, right? This part. Right?
Is that still under the assumption that R7 is much smaller than X7 plus?
Yes, see here, I put the T max with this one. I replace T max with this one, right? It's under this assumption.
Okay.
Under this assumption. Now let's simplify this one a little bit more. Let's simplify this one. Here, somewhere is R prime R over S. Let me see here. And we made a mistake here. Let me see. Yeah, I think I made a mistake here. See here, we made a mistake. This one is over S.
Oh, it is.
This is over S here. This is the S. See, look at here. We missed this part. You know, I just put the S here. So basically, here we should have an S. Here we should have an S. See, go correct that one. Here I missed the S here. See?
So then
Look
that's
at here. Here I didn't put the S. No, just correct this one. You should put the S here. This one doesn't have it.
So then in the circuit is it R prime R over S?
No, no,
The
here.
top?
For the P-max.
No, that one they are correct. Those one they are all correct. Those one they are all correct. The only thing is here. When I calculated TE, here I didn't put the S. Just I'm saying add the S here. The rest is correct. Now, let me see here. So, if you go back to the transformer, remember, almost the primary and the secondary, they have the same resistance, right? They're almost in the same order of magnitude. You know, maybe 2 times worst case, something like that, right? But look at here, I have R prime. This RTH ideally, let's get rid of the magnetization part, right? Let's say the middle branch is gone. Basically, RTH is going to be what? It's going to be RS, right? So, RS and R prime R over S. And S is a very small number. S is like 0.2%. So, either 2%, 3%, 4%, 5%. My point is, this one and this one, they're almost the same number. But this one is divided by a very small number, right? So, R prime R over S is very, very bigger than the ITH. It's a very, very valid assumption. You know what I'm saying? For example, RTH is 1 ohm, R prime SI is, for example, 0.5 ohm, right? Let's give you an example. For example, this is 1 ohm, this is a 0.5, right? But the S is 5%, for example. 0.5 divided by 5% is a 10. 10 is a 10 times of this one, right? My point is, we can ignore this one. We can, get rid of this one. So now, this equation becomes very, very simple. Very, very simple. So using this assumption, right? Using this assumption, let me put a little bit more, right? A little bit better. Thus I'm going to continue. R prime R over S is very, very bigger than RTH. So this one is said RTH plus R prime R over S is almost R prime R over S, right? Now let's write this equation again. T max over Ts is equal to R prime R over S plus XTH plus X prime R to the power of 2. Oh, this one is to the power of 2. Sorry. This is to the power of 2. To the power of 2, right? Divided by R prime R over S, and there is a 1 over 2 here. There is a 1 over 2 here. I'm going to put the 2 here in the denominator. 2 here. XTH plus X prime R. Right? Let's divide everything by this one. let's divide everything by this one. Numerator and denominator, right? So it's going to be 1. I'm going to take this s out of this one. It's going to be 1 over s2, right? Times r prime r over xth plus x prime r to the power of 2, right? I divided numerator and denominator by this value, right? So this one is going to be plus 1, right? Right?
Plus s squared.
Huh?
Right?
Huh?
Oh, never mind.
Yeah. So it's going to be 2 r prime r over s times this one divided by that. Right? So this one is going to cancel with this one, right? There's 1 here, right? Now let's see what it's going to be. How much is r prime r over this? Look at the word. How much is this? How much is this?
It's not.
S max, right? Is S max. So it's going to be 1 over S2 times 1 over S max to the power of 2 plus 1 divided by 2 divided by S times r prime r divided by this. How much is it? S max, right?
Should it be s max or 1 over s max in the numerator?
Huh?
It should be s max, right?
Yes, you're right. It should be S max. You're right. It should be S max to the power, right? So basically, T max over Ts is going to be this. Now let's time numerator and denominator by S2. Let's time it by S2. It's going to be S max to the power of 2 plus S2 divided by 2S S max. This equation. You use a lot for solving problems and those. This is very useful equation, very useful equation. We had two assumptions. The first one was we assumed this one is very smaller than this one, and the second one is this one. With these two assumptions, we got to this equation. So the last thing that I want to talk to about is, let's go back to the Thevenin circuit. For now, I said RTH, XTH, everything. Let's go based on the IEEE circuit to see how much is the RTH, how much is the XTH, if you want to use that circuit. So we went through everything. We find the characteristic of the machine, torque versus the speed versus the S. We went through the how much is the S max, how much is the T max, how much is the P max, how much is the SP max, right? We came up to this equation, which we are going to use it a lot for homeworks, and I don't know, maybe in exam, if you are going to see something like this, you have to use this equation. Now I'm going to go back to calculating RTH and XTH. I put the RTH, XTH everywhere. Now let's calculate how much they are. RTH and XTH, how much they are. And we're going to stop there today. And Tuesday I'm going to start to go over examples, Any questions so far?
With the T max over a T of S, does that get you like a percentage at what you are compared to your maximum?
No, this is for example, let's say what's the usefulness of this one. Let's say, I'm going to give you very quick, we have time. I'm going to tell you a very quick example, Let's say what we had over there, right? We calculated this, the starting I'm saying. I'm going to tell you to calculate how much is the R external you should put in the circuit. See how easy you can use this equation to calculate it. Let's say, for example, T max is 100, right? is 100 Newton meter, and TL, for example, is 50 Newton meter, right? So we want to calculate the starting resistor for this system, right? I'm going to put as much as resistor to have the maximum here. I want to move it like this. This is the maximum I can do. My T max would be here, right? Right? So let's go see how much is the S max. Actually, this one isn't clear. S max is going to be how much? 0, right? So maybe this is not a good example. This one would be 0. Yeah. No, this is not a good, for starting, this is not a good example. Oh, S is 1, sorry.
Yeah.
So S is 1, let's say, oh yeah. Let's say this way, you know, we said we want to have, for example, 70% of the torque at the starting, right, of T max. We want to have a T star, for example, right? We know the load is 50, maybe 50, let's say 70, for example, or 60. The load is 60, right? We want to have 70%, you know, starting torque, right? To be more than 60, right? So tell me how much resistor we should put in the circuit, right? Let's start using this equation. That's it. This S, see, we have 2 points always. One is the max, one is something else. Max is fixed, I cannot change anything, right? But here, it's starting, right? How much is S at the starting? 1, right? So let's put it here. I want to know how much my S max should be. How much should I move this one here? You know what I'm saying? Let's say this is a 60. This is a 60 Newton meter. I need to do this, right? To here would be 70, right? And this peak is 100, right? I want to know first. I want to know how much is my S max here. Because if I have the S max, look at here. If I have the S max, right? These are the motor parameters, right? I'm going to calculate how much resistance I need in my circuit, right? Let's say our prime R was 1 ohm. When I calculate it this way, it said 2 ohm, means I should add another ohm to that, right? You know what I'm saying? So let's say we use this equation, for example. We said 70%, right? Let's put it here. T max over 0.7 T max. Don't worry about it. We're going to go through examples a little later. It's going to be how much? I don't know how much is S max. Let's put S max here. Plus 1, right? Because we're at the starting. Over 2 S max. This one is going to cancel with this one. You go calculate S max. Right? So you say how much is it? Basically in this case, S max is R prime R plus R external XT over XTH plus X prime R. Right? How much is the R XT? It's going to be this one times that. Right? So I wanted this much, you know, starting torque. See, I didn't go through any of those equations. Just I use this one to calculate my external resistance in my circuit. We'll go through more examples, you know, Tuesday and in homework, and you're going to see more. Yeah.
So in that first equation, because you're going to end up with like a quadratic, is one number always going to be outside the range?
Yes. Yes. Okay. Always going to be one or other one. For example, it's going to be negative S. For example, it's going to be more negative S is going to be over there on that side, right?
Or like
yeah, we have something between 1 to 0 would be, you know, acceptable, you know, because you know here it is 1, right? Here is 1, here is 0. We're not going to have two numbers. 1 is going to happen. Okay. Now let's calculate the RTH and XTH. I'm going to go with the IEEE circuit. IEEE circuit was like this. And really this part doesn't matter, right? Because we don't care about this part. We want to calculate this part. This is a VS. RS, XS, XM, right? So I'm going to replace this part with this. Forget that, we don't care about this part now. So basically it's going to be VTH RTH XTH, right? We want to see how much are these values, right? So we're going to see how much is the R. We're going to see how much is the VTH, how much is the RTH, how much is the XTH. Those values we want to calculate.
First
Oh,
one's
no,
R.
oh yeah, this is R. Right? So how much is a VTH? Let's calculate this one. Basically, VTH is going to be a voltage divider between this and this, right? It's going to be JXM over RS plus JXS plus XM times VS, right? You know, RS, XM, go back to the transformer, XM is a big number, right? So RS is very, very smaller than XS plus XM, right? So basically, VTH is equal to XM over XS plus XM PS. Let's call this one KTH. KTH. So basically VTH is equal to KTH times VS, which KTH is this value, right? And still also, you know, XS is much smaller than XM, right? So basically VTH should be very, very, very close to VS value, right? So we calculated this one. Now, let's get to the RTH and XTH. How much is a ZTH? Let me start from here. How much is a ZTH? This one parallel with this, right? Basically JXM times this, right? It's going to be JXM times RS plus JXS over RS plus JXM plus
Excess.
right? XS. Did I put it good? Parallel is going to be this times this, right? Divided by that. Again, let's forget RS, right? Compared to this term, right? So this one is almost is equal to JXM times R. Forget the J. It's going to be RS plus JXS over what? Right. So the real part is going to be RTH. The imaginary part is going to be XTH, right? So RTH is going to be how much? XM over XM plus XS RS, right? What was this? KTH, right? It's going to be KTH RS. Let's go with the XTH. How much is the XTH? XM times the, I got rid of the J, right? I'm writing the value. XTH is going to be XM XS over XM plus XS, right? So basically this is like XM parallel with XS, right? And you know XS is XS is a leakage, right? XM is a magnetization, right? When we have a XS is a very small number, XM is a very big number, right? What is the result? XS, right? So this one is almost XS. This one is almost XS.
Why can we assume that RC goes to infinity, or is that just?
No, this is just is not infinity, you know. But we first of all, RC is a fake resistor, right? we just put that one there to model the core loss. But as I say, go check the transformer examples we had. See, RC usually is a very big number. Very big number, and we can get it up, you know. So, but another thing is that RC is a fake thing. We put there to model the. In reality, there is no RC. Let's put it up on the side, just representing the core loss. So I think we are good for today. There was lots of equation. We went over it. Tuesday, there is a little bit more to talk about it. It is there are like a transformers. We have to be able to measure XS, RS, XM, R prime R, X prime R. Those values, like transformer, we have an open circuit and short circuit test. Here we have a block rotor test and no load test. We do those tests to measure these values. After that, we are done with the induction machine. I'm going to go over the examples, to some examples. Tuesday or maybe part of the, not Thursday. Thursday I want to teach synchronous machine, and again next Tuesday after, again we can go work on some more examples, on the induction machine.